Beyond the Multiverse, Parallel Realities and Hidden Universes. By David Rousseau. Introduction. The Universe Beyond the Universe. Some dialogue in this audiobook has been reconstructed from memory to help illustrate key ideas. These conversations reflect the substance of real discussions, though the exact wording may vary. Me, Doctor. Thinking about these possibilities makes life feel bigger somehow. Doctor, it can. Whether or not multiple universes exist, imagining them reminds us that reality may hold far more possibilities than we can see. Me, almost like every moment holds a new direction. Doctor, that's a good way to see it. For most of human history, the universe was thought to be everything that existed. The stars overhead, the planets wandering through the night sky, and the vast dark spaces between them formed the complete stage of reality. Beyond that cosmic stage, there was simply nothing. Ancient civilizations looked up at the heavens and imagined mythological realms hidden among the stars. Later, as science advanced, telescopes revealed a universe far larger than anyone had ever suspected. The Milky Way turned out to be only one galaxy among billions, each containing hundreds of billions of stars. Yet even this enormous universe might not be the whole story. Over the past century, modern physics has begun to hint at something even more extraordinary: the possibility that our universe could be just one region within a much larger cosmic structure, a structure that may contain countless other universes, each with its own history, its own physical laws, and perhaps its own forms of life. This idea is known as the multiverse. At first glance, the concept sounds like science fiction. Entire universes beyond our own, realities that branch and multiply, worlds hidden in extra dimensions or born from black holes. But many of these ideas do not come from fantasy. They emerge naturally from some of the most serious attempts to understand the fundamental laws of physics. When physicists study quantum mechanics, the strange theory that governs the behavior of particles, they encounter a world ruled not by certainty, but by probabilities. Some interpretations of quantum theory suggest that every possible outcome of an event might actually occur, each in its own branching universe. Cosmologists studying the birth of the universe have discovered that the Big Bang may not have been a unique event. Certain models of cosmic inflation suggest that new universes could constantly form, like bubbles in an ever-expanding cosmic foam. Meanwhile, theories such as string theory propose that reality may contain additional spatial dimensions beyond the three we experience, separated not by distance, but by the hidden geometry of space itself. Even more radical possibilities have been proposed. Some scientists suggest that reality might ultimately be made of information, like a vast computational structure. Others have explored whether our universe could be a detailed simulation created by an advanced civilization. Still others argue that mathematics itself may generate reality, that every possible set of physical laws corresponds to a real universe somewhere in a limitless mathematical landscape. These ideas are explored by some of the most influential thinkers in modern physics, including Max Tegmark, Brian Greene, and Roger Penrose. While many of their theories remain speculative, they are grounded in genuine attempts to understand the deepest structure of reality. Of course, not every proposal discussed in this audiobook has equal scientific support. Some are well-developed theories actively studied by physicists. Others are philosophical interpretations of what those theories might imply. But together they open the door to one of the most fascinating questions humanity has ever asked: is our universe the only one that exists? Or could reality be vastly larger, filled with parallel worlds, hidden dimensions, and cosmic possibilities far beyond our everyday experience? In the chapters ahead, we will explore a wide range of ideas about the multiverse. We will examine how quantum mechanics might create branching realities. We will look at theories suggesting that universes can be born, destroyed, and reborn across unimaginable spans of time. We will explore the possibility of mirror worlds, simulated realities, and hidden cosmic structures made of dark matter. Some of these ideas may eventually be confirmed through observation or experiment. Others may remain forever beyond our ability to test. Yet even the act of exploring them has value, because every time science expands its view of the cosmos, humanity's understanding of its place within that cosmos changes as well. A few thousand years ago, we believed Earth was the center of everything. A few hundred years ago, we learned that our planet orbits an ordinary star. A few decades ago, we discovered that our galaxy is only one among billions. Now, we are beginning to ask an even larger question. What if our entire universe is only one small piece of a far greater reality? If that is true, then the cosmos may be more vast, more complex, and more mysterious than we have ever imagined, and the journey to understand it has only just begun. Chapter 1: Quantum Immortality. At the smallest scales of reality, the universe behaves in ways that seem almost impossible to understand. Using ordinary intuition, the strange rules governing atoms and subatomic particles are described by a branch of physics known as quantum mechanics. Unlike the predictable motion of planets or falling objects, quantum mechanics describes a world ruled by probabilities. Particles do not always exist in one definite state. Instead, they can exist in multiple possible states at once until they are measured or observed. This idea is often illustrated through a concept known as superposition. In superposition, a particle can exist in several potential conditions, simultaneously different positions, different energies, even different physical properties. Only when an observation is made does the particle appear to choose a specific outcome. For decades, physicists struggled to understand what this strange behavior meant for the nature of reality itself. One of the most famous attempts to explain it came from the physicist Hugh Everett III in 1957. Everett proposed a radical idea, now known as the many worlds interpretation. According to this interpretation, the universe never collapses into a single outcome when a quantum event occurs. Instead, reality branches. Every possible outcome of a quantum event happens, but each one unfolds in its own separate branch of the universe. Imagine flipping a coin. In everyday experience, the coin lands either heads or tails. But in the many worlds interpretation, both outcomes occur. The universe splits into two branches, one in which the coin lands heads, and another in which it lands tails. From the perspective of an observer in either branch, only one outcome is visible. The other branch becomes part of a parallel reality. If this idea is correct, then branching events would occur constantly throughout the universe whenever quantum processes produce multiple possible outcomes. Over time, these branches could multiply into an enormous network of parallel histories. Some physicists and philosophers have wondered whether this branching structure might have surprising implications for consciousness. One speculative concept that emerges from this idea is called quantum immortality. The concept suggests that if consciousness always continues along the branch of reality in which a person survives, an observer might only experience outcomes where they remain alive. In branches where death occurs, that observer would simply no longer experience events. From their subjective perspective, awareness would continue only along survival paths. It is important to emphasize that quantum immortality is not an established scientific theory. Most physicists treat it as a thought experiment rather than a realistic description of how life and death work. There is currently no experimental evidence supporting the idea, and many researchers argue that it misunderstands how quantum mechanics and consciousness interact. However, the concept highlights something profound about the many worlds interpretation. If reality truly branches into countless versions, then there could exist many different versions of every person, each living out different possibilities shaped by the countless quantum events that occur every moment. In one branch of reality, a small decision may lead to one future. In another branch, the same moment might unfold differently, producing an entirely different path. From a cosmic perspective, the universe might resemble an ever-growing tree of possibilities. Every quantum event becomes a branching point. Every branch becomes a different history, and somewhere within that vast structure could exist countless variations of worlds that look similar to our own, alongside others that are dramatically different. Whether the many worlds interpretation is correct remains one of the most debated questions in modern physics. Yet even as a possibility, it invites us to reconsider something fundamental about reality. What we experience as a single, continuous world might actually be only one thread within an immense tapestry of parallel outcomes. And if that is true, then the universe may be far more expansive, not only across space, but across possibility itself. Chapter 2: Mirror Universes. Physics often uncovers the hidden symmetries that structure the cosmos. In scientific terms, a symmetry is a transformation that leaves nature's fundamental laws unchanged. For instance, whether an experiment is conducted today or a millennium from now, on Earth or in a distant star system, the laws of physics hold the same. These symmetries provide the mathematical framework underlying modern physics. Yet, nature doesn't always conform to our expectations. During the mid-1900s, physicists realized that some symmetries, long assumed to be exact, could actually be broken under specific conditions. This revelation hinted that the universe was far more intricate than previously imagined. A striking case involves parity symmetry. Parity is the principle that physical laws should be unchanged if spatial coordinates are inverted. Essentially, if the universe were viewed through a mirror, perfect parity symmetry would mean that a mirrored version of reality behaves identically to ours. Experiments in the 1950s, however, revealed a surprise. Certain subatomic interactions defy parity symmetry. In particular, the weak nuclear force, the mechanism behind some forms of radioactive decay, operates differently in a mirror-reflected system. This discovery startled physicists and reshaped our understanding of symmetry in nature. The key experiment was led by physicist Chen-Ching Wu, whose observations demonstrated that the universe distinguishes left from right in ways never anticipated. This prompted theorists to speculate: if parity symmetry is broken in our universe, could a corresponding symmetry exist elsewhere? Enter the concept of a mirror universe, a parallel reality composed of mirrored versions of familiar particles and forces. In such a universe, fundamental interactions would appear reversed. Particles spinning one way here might spin the opposite way there. Asymmetries we observe might balance out when both universes are considered together. Within this framework, our universe is only a fraction of a broader cosmic system. A mirror universe could host its own stars, galaxies, and perhaps planets, yet remain invisible because mirror particles might interact extremely weakly or not at all with ordinary matter. Some researchers even propose that mirror matter could explain one of cosmology's greatest enigmas, dark matter. Astronomers have long noted that visible matter cannot fully account for the gravitational effects observed in galaxies. Unseen mass appears to dominate the cosmic landscape. If a mirror universe exists, its hidden matter could exert gravitational influence on ours while remaining undetectable. Entire galactic systems might coexist in tandem with our own, invisible yet gravitationally entwined. Currently, mirror universes remain speculative. No direct evidence of mirror particles or galaxies has been observed. Nevertheless, the concept illustrates the central role of symmetry in physics. By examining why certain symmetries fail and how they might be restored in broader frameworks, scientists gain insight into the deeper fabric of reality. The universe around us may seem orderly and predictable, yet beneath this surface lie hidden layers of structure, possibly other realms that reflect our own like a cosmic mirror. If such mirrored worlds exist, they remind us of a profound truth. The universe we see may represent only one side of a grander reflection. Chapter 3: The Cyclic Universe. For centuries, humans have pictured the universe as having a singular origin, a unique explosive event known as the Big Bang. From that moment, space expanded, matter coalesced, stars ignited, and galaxies formed. This vision of a one-time beginning shaped not only scientific thinking, but also our sense of cosmic history. But what if the universe doesn't adhere to a simple linear timeline? What if cosmic history is not a single, unfolding event, but a recurring cycle of creation, destruction, and renewal? This is the essence of cyclic cosmology. According to these ideas, the universe repeatedly passes through phases of expansion, cooling, contraction, and rebirth. Each Big Bang might not mark the ultimate beginning, but could represent the latest phase in an endless chain of cosmic eras. A prominent version of this theory is Roger Penrose's conformal cyclic cosmology. In his model, the universe moves through immense cycles, or eons, separated by stretches of time so vast they are almost impossible to imagine. Each eon begins with a hot, dense state and ends in a near-empty universe dominated by radiation. Over time, cosmic scales stretch so thoroughly that distinctions between large and small fade, allowing one eon to transition smoothly into the next. The implications are staggering. If the universe is cyclic, what we perceive as the beginning of time be just one chapter in an infinite saga. The cosmos would have no true origin, only a succession of transformations that stretch endlessly forward and backward. Cyclic models also offer solutions to long-standing cosmological puzzles. They help explain the remarkable uniformity of the universe and why certain cosmic structures appear as they do. Each cycle effectively resets the cosmic conditions while leaving subtle imprints of previous eons. This perspective challenges conventional notions of time. Instead of a straight arrow from birth to death, time could loop, bend, or reset, with the universe eternally regenerating itself. Galaxies, life, and even the laws of physics might be part of this recurring rhythm. Although still speculative, cyclic cosmology reveals a profound possibility. The universe may not be finite or confined to a single narrative. Instead, it may be an eternal process, where every ending becomes a beginning and every beginning carries echoes of the past. Seen this way, our cosmic home is both ancient and endlessly renewing a universe that never truly perishes, but beats with a rhythm stretching across eternity. Chapter for a digital universes. What if reality itself isn't made of matter at all but of information? This radical idea has been proposed by some of the most imaginative physicists of the 20th century, and it challenges our very notion of what it means to exist. The concept is often summarized by the phrase, coined by physicist John Archibald Wheeler, if from bit. In Wheeler's vision, the physical universe arises from fundamental units of information, binary decisions, yes or no, 1 or 0. Everything we see, touch, and measure could emerge from these underlying informational building blocks. Think of it like a cosmic computer. In a computer, lines of code and data create simulations of worlds, characters, and events. Similarly, Wheeler suggested, the universe might operate like a computation on a far larger scale, with its own rules encoded as information. From this perspective, particles, forces, space, and time could be emergent phenomena, patterns arising from a more fundamental informational structure. What appears solid and continuous is actually a vast network of discrete bits, interacting according to the rules of the cosmic program. If reality is fundamentally informational, the implications are staggering. Entire universes could exist as different informational structures, each with its own set of rules and patterns. These universes might follow laws completely unlike our own or behave in ways we cannot even imagine. Some theorists have speculated that this view could help reconcile quantum mechanics with general relativity by framing the universe as a computational system. The apparent contradictions between these two pillars of physics could be interpreted as different layers of the same informational architecture. Even more provocatively, a digital view of reality invites philosophical questions. Are we, and everything around us, part of a cosmic program? Could consciousness itself emerge from the processing of information, just as life emerges from biological code? While these ideas remain speculative, they push the boundaries of physics and philosophy alike. They ask us to reconsider not just the material universe, but the nature of existence itself. In a digital universe, the cosmos is not simply a collection of particles and forces. It is a network of information, a dynamic system where reality unfolds according to rules that may be more abstract, more mathematical, and more profound than anything we can directly observe. In such a universe, the familiar world around us is only the surface of something deeper, a hidden informational landscape where entire realities could exist side by side, waiting to be discovered by thought, observation, or imagination. Chapter 5: Assimilated Universes. Imagine, for a moment, that everything you see, touch, and experience is part of a highly detailed simulation, that the universe itself might not be real in the way we think, but instead a sophisticated creation generated by an advanced intelligence. This is the idea behind simulated universes, a concept that has moved from science fiction into serious philosophical and scientific discussion. One of the most influential thinkers to explore this possibility is philosopher Nick Bostrom. In his famous 2003 paper, Bostrom proposed a thought experiment. If civilizations eventually develop the computing power to simulate entire universes, and if even a fraction of them choose to do so, then the number of simulated realities could vastly outnumber real ones. If that is true, the odds suggest that we might ourselves be living in a simulation. Every particle, every galaxy, every law of physics could be part of a grand, computational program designed by some intelligence far beyond our comprehension. This raises profound questions about reality, free will, and consciousness. If our universe is simulated, what does it mean to be alive? Are our choices truly our own? Or are they predetermined by the rules of the simulation? Could there be other layers of reality beyond the one we perceive? While the idea of a simulated universe may sound fantastical, it is grounded in serious logic. Advances in computing, artificial intelligence, and virtual reality show that creating detailed, interactive worlds is increasingly possible. In a few centuries, it may be technologically feasible to simulate entire civilizations with conscious beings. Physicists and cosmologists have even begun to explore whether our universe shows signs of computational constraints. Are the constants of physics fine-tuned because of the needs of a simulation? Could cosmic phenomena reveal hints that the universe is discretized, pixelated at its smallest scales? These are open questions, but they highlight that the hypothesis is not purely science fiction. It is a legitimate framework for inquiry. Whether or not our reality is simulated, the concept stretches the imagination and challenges the way we think about existence. It suggests that what we consider natural or fundamental might itself be a product of design, and that layers of reality could extend far beyond what our senses and instruments detect. In this view, our universe becomes more than a collection of stars and particles. It becomes a program, a construct, a story running in some grand cosmic computer, inviting us to wonder just how deep the rabbit hole of reality truly goes. Chapter 6. Universes with Extra Dimensions. We experience the universe in 3 dimensions of space length, width, and height, and 1 dimension of time. This 4-dimensional framework shapes everything from the motion of planets to the trajectory of a thrown ball. It feels complete, intuitive, and absolute. Yet modern theoretical physics suggests that this familiar view might be just the tip of the iceberg. Beyond the dimensions we perceive, there could exist additional spatial dimensions, hidden realms folded or compacted so tightly that we cannot detect them with ordinary senses or instruments. One of the leading frameworks proposing extra dimensions is string theory, explored by physicists such as Edward Witten. In string theory, the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings. The way these strings vibrate determines the properties of particles, forces, and even space-time itself. For the mathematics of string theory to work consistently, the universe must have more than 4 dimensions, sometimes as many as 10 or even 11. These extra dimensions could be curled up at scales far smaller than an atom, invisible to current experiments, yet crucial in shaping the behavior of the cosmos. If extra dimensions exist, they may contain entire parallel universes, existing not side by side in space, but in dimensions beyond our perception. These universes could follow physical laws very different from our own, with different constants, particle interactions, or even entirely new forms of matter. They would be hidden not by distance, but by the very geometry of higher dimensional space. The idea also offers potential explanations for some of physics' deepest mysteries. For example, extra dimensions could help unify gravity with quantum mechanics, reveal why fundamental forces have the strengths they do, or suggest mechanisms for dark matter and other unseen phenomena. For us, these dimensions may remain forever imperceptible, yet they could be the stage on which the multiverse unfolds, a hidden architecture of reality. Beneath the world we experience, the universe might not be a single 3-dimensional stage, but a vast, multi-layered structure with realities stacked along dimensions we cannot sense. In this view, our familiar universe is just one slice of a far larger, more complex reality. Entire worlds could exist beyond the reach of light, matter, and human perception, connected only through the subtle fabric of higher dimensional space. If this is true, the cosmos is not simply vast, it is multidimensional, layered, and infinitely stranger than our senses can reveal. Chapter 7. The Shadow Universe. One of the greatest mysteries in modern cosmology is the nature of dark matter. Scientists know it exists because of the gravitational effects it exerts on galaxies and clusters of galaxies. Galaxies spin faster than they should if only visible matter were present, and large-scale, cosmic structures form in ways that require far more mass than we can see. Yet dark matter does not emit, absorb, or reflect light, making it completely invisible to telescopes. This mysterious substance makes up roughly 27% of the universe, vastly outweighing the ordinary matter that forms stars, planets, and life. But what is dark matter made of? That question remains unanswered. Some physicists have proposed an extraordinary possibility, that dark matter is not just unseen matter in our universe, but is part of a shadow universe, a hidden realm that exists alongside our own. In this scenario, the shadow universe could be composed of mirror particles, which behave similarly to ordinary matter, but interact only weakly with it, primarily through gravity. If this theory is correct, then the cosmos we observe might only be one side of a larger reality. Every galaxy, star, and planet could have a mirror counterpart in the shadow universe. We would never see these worlds directly, but their gravitational influence would shape the motion of galaxies and the evolution of cosmic structures. The idea of a shadow universe also helps explain why dark matter is so elusive. Ordinary experiments that detect electromagnetic forces, light, radio waves, or X-rays would be blind to mirror matter. Yet the gravitational fingerprints of this hidden world could be all around us, subtly guiding the formation of galaxies, clusters, and cosmic filaments. Some researchers speculate that the shadow universe could be just one of many hidden layers of reality, parallel to ours in a higher dimensional or mirrored space. It would exist in tandem with the visible cosmos, largely invisible, yet intimately connected through the fabric of space-time. While the shadow universe remains speculative, it demonstrates how cosmology often pushes beyond what we can see. The universe is not simply what is visible through telescopes. It may contain hidden realms that exert profound influence, shaping the very structure of reality without ever revealing themselves directly. In this light, the universe we know might be only half the story. A vast, invisible mirror could exist alongside us, a shadow realm quietly orchestrating the cosmic dance of galaxies, stars, and planets. And if that is true, the cosmos is far more mysterious and more beautiful than we have ever imagined. Chapter 8. The Time-Reversed Universe. We often think of time as a river flowing in a single direction, from past to present, from birth to death, from the Big Bang to the distant future. This arrow of time shapes nearly every aspect of our experience. Ice melts rather than spontaneously freezing in a warm room. Stars age and eventually burn out. We grow older with each passing year. Everywhere we look, the world seems to move forward along a single, irreversible path. Yet modern cosmology suggests that time itself may not be as absolute as it appears. Some theoretical models propose the existence of a time-reversed universe, a cosmos in which the arrow of time flows opposite to our own. In these ideas, the Big Bang may not represent the absolute beginning of everything. Instead, it could act as a kind of midpoint between two universes that expand away from one another in opposite temporal directions. In our universe, time flows forward from the Big Bang toward an ever-expanding future. In the mirror universe, however, time would move in the opposite direction relative to ours. From our perspective, events there would seem to unfold backward. The concept may feel strange at first, but the intuition behind it is surprisingly familiar. Comedian George Carlin once joked about how life might work if it ran in reverse. You would start old and retired, grow younger each year, leave work to return to school, and eventually end your journey as a baby. While intended as humor, the idea captures the oddness of imagining events unfolding in the opposite order from what we expect. Physics offers a more serious version of this reversal. At the most fundamental level, many of the laws that govern the universe are time-symmetric. Equations describing gravity, electromagnetism, and even much of quantum physics often work equally well whether time moves forward or backward. In principle, the microscopic laws of nature do not prefer a particular direction, yet the world we observe clearly does. This preference is tied to one of the most important principles in physics, entropy. According to the second law of thermodynamics, entropy, a measure of disorder, or the number of possible arrangements in a system, tends to increase over time. A tidy room becomes messy. A hot cup of coffee cools. Broken glass does not spontaneously reassemble. Entropy gives time its arrow. A time-reversed universe offers one possible explanation for why this arrow exists. In some cosmological models, the Big Bang begins in a state of extremely low entropy. From that central point, entropy increases in both temporal directions. In other words, two universes emerge from the same boundary condition, each experiencing entropy increasing along its own arrow of time. To observers in our universe, the other cosmos would appear to run backward. But to observers within that universe, if any existed, time would feel perfectly normal. Their past would lie toward what we call the Big Bang, and their future would extend in the direction opposite to ours. They would experience causality, memory, and the passage of time almost as naturally as we do from our viewpoint. However, their universe might look bizarre. Processes that normally move toward disorder here could appear to reverse. Gas clouds might seem to assemble into stars rather than dispersing from them. Heat might appear to flow from colder regions to warmer ones. Structures could form in ways that look like a film played in reverse. But the inhabitants of that universe would not perceive anything unusual. Their own arrow of time, defined by increasing entropy, would make events unfold in a consistent and meaningful sequence. Their memories would form in the direction of their future, just as ours do. This idea highlights something profound. The direction of time may not be a universal property of reality. Instead, it may emerge from the initial conditions of the universe and if this picture is correct, the Big Bang becomes something more subtle than a beginning. It becomes a boundary, a moment of minimal entropy from which two temporal directions emerge. One universe expands toward what we call the future. The other expands toward what we perceive as the past. Together they form a kind of cosmic symmetry. Physicists continue to explore these possibilities using mathematical models and observations of the early universe. While a time-reversed cosmos remains speculative, it demonstrates how deeply modern cosmology challenges our everyday assumptions. Concepts like past and future, cause and effect, and even the flow of time itself may depend on perspective within the larger structure of the universe. If such mirror universes exist, they would remind us that reality is often stranger than intuition allows. Our familiar experience of time, steady, forward-moving, and irreversible, might represent only one branch of a much larger temporal landscape. The cosmos, it seems, may not only stretch across unimaginable distances in space, it may also extend across directions of time that our everyday experience barely allows us to imagine. Chapter 9: Consciousness Universes. Quantum physics has long challenged our understanding of reality, and one of its most puzzling features is the role of observation. At the quantum level, particles do not exist in a single, definite state until they are measured. Instead, they occupy a superposition of multiple possibilities, existing in all allowed states at once. Only when an observation is made does the particle appear to choose a specific outcome. This strange behavior raises a profound question. What role does consciousness play in shaping reality? Some interpretations of quantum mechanics suggest that the act of measurement or observation does more than reveal the state of a system. It may, in some sense, help define it. The most famous formulation of this idea comes from the Copenhagen interpretation, associated with physicist Niels Bohr. In this view, the physical properties of quantum systems are not fully determined until observed. Reality, it seems, depends on the interaction between the observer and the observed. From this perspective, consciousness could be more than a passive witness. It might play a subtle, yet fundamental, role in the unfolding of the universe. Some philosophers and physicists have speculated further. Could consciousness itself give rise to branching realities, parallel worlds, or even entire universes? These ideas are highly speculative and controversial. Most scientists do not believe that human minds literally create the universe, yet the connection between observation and outcome remains one of quantum mechanics' most intriguing puzzles. It forces us to reconsider the boundaries between mind and matter, subject and object. In certain thought experiments, the implications of consciousness become even stranger. If reality splits into multiple branches at every quantum decision, as suggested by the many worlds interpretation, then the observer is not just witnessing a single outcome but experiencing a vast network of parallel possibilities. Each act of observation might correspond to one path through a complex multiverse, with countless other versions of reality unfolding simultaneously. The study of consciousness universes challenges the very way we understand existence. It suggests that awareness might be deeply entwined with the structure of reality, that the act of seeing, measuring, or thinking could influence the universe in ways we are only beginning to grasp. Whether these ideas are physically real or remain philosophical musings, they illuminate a remarkable truth. Our understanding of the cosmos is inseparable from our understanding of ourselves. In the quantum universe, mind and matter may be linked more intimately than we have ever imagined, and the mysteries of consciousness may reveal truths about the very nature of existence. Chapter 10. The Ultimate Multiverse. Imagine a reality so vast that every possible universe exists, every variation of physical laws, every configuration of matter, every conceivable history. This is the idea of the ultimate multiverse, a concept proposed by physicist Max Tegmark. In this framework, every mathematically consistent structure corresponds to a real universe, forming a limitless cosmic ensemble. Unlike parallel worlds that emerge from quantum events or hidden dimensions, the ultimate multiverse contains every possible universe. If a set of physical laws can exist logically, somewhere it does exist. In one universe, gravity might be stronger, stars could burn in colors we cannot imagine, or time could behave in ways that defy our intuition. In another, matter might form patterns completely alien to our understanding. Tegmark categorizes this vision as a level for multiverse, the most radical level in his hierarchy, while other multiverse models, such as quantum branches or cyclic universes, still share features with our own reality. The level for multiverse encompasses all possible realities, regardless of how different or bizarre they might be. The implications are staggering. It means that for every decision, every event, and every outcome imaginable, there exists a universe where it happens. Every possible history, both probable and improbable, unfolds somewhere in this infinite landscape. Every variation of you, every version of Earth, every alternate cosmos already exists. This idea also raises deep philosophical questions. If all possibilities exist, what does that mean for identity, choice, and meaning? Are our actions significant in a multiverse where every alternative occurs? And if every universe exists as a mathematical structure, what is the nature of existence itself? From a scientific perspective, the ultimate multiverse stretches the boundaries of physics into the realm of mathematical reality. It suggests that mathematics is not just a language to describe the universe, but a foundational blueprint of existence. Reality itself may be a vast landscape of abstract structures, each as real as our own universe. Whether or not we can ever observe these other universes, contemplating them expands the limits of human thought. It challenges our notions of possibility, forcing us to imagine a cosmos far stranger, more diverse, and more infinite than we have ever experienced. In the level for multiverse, the word impossible loses its meaning. Every conceivable reality exists somewhere. The universe we inhabit is not the only one, it is just one thread in an infinite, unimaginable tapestry of existence. Conclusion: the endless cosmos. Throughout this journey, we have explored ideas that challenge everything we thought we knew about reality, from the branching paths of quantum immortality to the hidden reflections of mirror universes. We have seen that the cosmos may be far stranger than everyday experience suggests. We considered cyclic universes, where the cosmos endlessly dies and is reborn, and digital universes, where reality itself might be woven from information. We examined the possibility that our world could be simulated, a carefully constructed program running on a cosmic computer. we explored extra dimensions that hide parallel realities, just beyond perception and the shadow universe, where unseen matter may shape our cosmos in ways we cannot detect. We contemplated time-reversed universes, where the arrow of time flows in the opposite direction, and consciousness universes, where the act of observation could influence the unfolding of reality. Finally, we encountered the ultimate multiverse, a vast landscape in which every logically possible universe exists as a real mathematical structure. Some of these theories may one day be tested or confirmed. Others may remain purely speculative or philosophical. Yet even without definitive answers, exploring these possibilities expands the limits of human imagination. It reminds us that our universe, enormous as it seems, might be only a tiny fragment of a far greater cosmic reality. These ideas inspire wonder and humility. They suggest that reality is not confined to the observable or the familiar. There may be hidden layers, branching possibilities, and universes beyond counting, each with its own rules, histories, and forms of existence. In contemplating the multiverse, we are also confronting the profound question of our own place within it. Are we unique, or one version among countless variations? Are the laws of nature fixed, or do they change across realities? And what does it mean to exist in a cosmos that may stretch infinitely in space, time, and possibility? The universe is vast, yet the multiverse may be infinite, a boundless tapestry of realities, waiting to be imagined, explored, and understood. Every chapter of science, every question of philosophy, every spark of curiosity brings us a little closer to glimpsing the full scope of existence. In the end, the greatest revelation may be this: our journey of discovery is far from over. The cosmos continues to unfold, and with each step, we find that the universe is not a fixed stage, but a living, infinite frontier, full of mysteries beyond our wildest dreams.